Great. So, yeah, thanks ever so much. I really appreciated being invited here. It's my first time in Stockholm, so fantastic to be here with all of you. My session today is about how Amazon EventBridge can transform serverless development. Now, for those of you who don't know me, I'm a developer advocate for the AWS serverless team. And before I was a DA, I was a software engineer for a long time, and then a product manager for quite a few years. And before this, I worked at lots of different startups and places like Rackspace and Morgan Stanley. But really, most importantly, I've been a serverless geek for the last couple of years. So I've built lots of end-to-end applications with all these different tools. And what drew me to serverless really is that all of these cool tools let us solve customer problems much more easily with less code. So EventBridge came up as something fairly new this year, and I immediately jumped all over it, and I think it has some really interesting benefits for how we can use it in serverless. But first, let's talk about some of the problems we have in development today. So monoliths are everywhere, and it doesn't matter how much we keep trying to break them down, they keep coming back. And part of the reason for this is that they kind of get a bad rap. When you think about it, monoliths are easy to build and reason about. They often have a single ACID-compliant database, and everything's happening in the same memory space. Whereas distributed systems are much, much harder to get your head around. But the problem is that monoliths don't scale at all. They don't scale in terms of amount of traffic or number of engineers. So if you have a large project with dozens or hundreds of engineers, you have little choice but to really move towards a microservice model in order to get all the benefits of feature velocity out of your team. But monoliths do keep showing up, and let me prove this to you. So this is a standard synchronous API, and I'm sure we've all built plenty of these. So a client request comes in, the post order hits an order service, it turns around and posts an invoice service request. The invoice service does some work, and maybe creates an invoice number, and then it returns with a status code, and that returns back to the client, and everybody's happy. Great, no monolith. And then what happens is that it's fine right now because we have a simple two-service system. And as long as it stays this way, there'll be no monolith. But what happens is that over time, there are more services that get added, and the order service has to integrate more and more, and it starts to get more responsibilities. So downstream services will publish APIs, but the order service is now responsible for hooking them up each time. And the order service also has to understand retry semantics and error logic and that kind of thing. And I'm sure nobody in this room has ever developed a backwards incompatible API, but if one of those downstream services did, the order service would be on the hook for making all the updates. Now, long term, more and more of these systems out there need data from the order service. So what happens is, in this model, these teams become blocked by the order service team to implement. And they're not as independent as they once were. And they're responsible now for this integration cost and the friction that starts to develop. And so, over time, guess what? We're back to having a monolith. The decoupling is gone. So what can we do about this? Here's the second problem. So, as APIs develop into complex workflows, it can be very difficult to make sure that each service has the right state. And let me explain. So we talked about the happy path earlier, but here's another one for you. Here's a simple e-commerce application. In this happy path, the order service receives an order, and it will trigger the invoice service, and then maybe the payment gateway and a forecasting service. The payment system, once it's then been cleared, will then send an order to, or send a message to the fulfillment service where someone in a warehouse will put something in a box, and then when that's done, they'll trigger a request to a shipping service. And in this situation, this is all fine. But what happens when the fulfillment center is out of stock? Someone's physically gone to the shelf in the fulfillment center, and the product is not there. Well, the fulfillment center may have to then send a message to the order service, and then they send a message to payment because they have to reverse the payment or issue a part credit or something like that. And then the shipping service has probably already been told because it was a physical problem, not a problem with the software. So fulfillment sent a message to forecasting that, hey, we've got a problem, that number's not right anymore. Shipping now, for some reason, sends a message to the invoice service because they don't know about how to deal with this. And it turns out the forecasting service is not able to accept these adjustments, so the numbers are just wrong. And somebody has to go in and manually update things. Here's another one that's even more likely in my experience. Imagine your team works on the payment service, but now you weren't told that another service has come along, in this case, a rewards service. And what happens now when the fulfillment service has a problem? Well, the fulfillment service probably orchestrates a bunch of things. So they send a message just like before, and all these things are going off, and the shipping service isn't involved this time. But the end result is the rewards service never finds out. And so a cancelled order in this case actually results in a reward for a customer. Now what happens when the rewards service has another vendor? They just change vendors completely. So they have another API added, and they have a link between the old API and the new API. And what you find is, as these systems mature and develop, it just becomes spaghetti. It becomes harder and harder to orchestrate the flows between these different services. Here's one more problem. Let's talk about availability in these systems. So back to our ordering system, where your team is managing the payment system. There are a couple of potential problems. One is performance mismatch. So it takes longer to process payments than to take orders. So in very busy times of year, like Black Friday or Thanksgiving or Christmas, basically orders are coming in and you're not keeping up with the order service. So what happens is that you're putting a fast service in front of a slow service in this synchronous API coupling, and you're slowing down the service in front of you, and it tends to lead to a world of pain. The second problem is to do with outages. So in this very tight coupled synchronous model, when your payment system goes down, the order service also goes down. So the availability numbers for the total system start to look worse and worse because these things are so tightly coupled. And any sort of failure in one part of the system starts to look like a failure for the total system from the point of view of a customer. So how can events help with these three problems? Well, first of all, what is an event? An event is simply a signal that a system state has changed. In modern systems, often that's a blob of JSON, and it'll contain something about the change maybe and the new state of the system. Events are facts, they're immutable, they're observable, and they're temporal. When they happen matters to the system. But we're really interested in the fact that they're observable and not directed. So in a command-directed model, what happens is the person on the left says to the person on the right, please go ahead and make an invoice. And the person on the right then goes away and does the work. And as there are more and more people on the right, it's incumbent on the person on the left to keep track of what all these people are doing. Now, events being observable mean that they're simply observed by other people around them. So now that the person on the left says, well, customer X just ordered a widget, and now someone in the back heard that and decides to add it to a sales report, another person hears it and decides to send an invoice, and two people hear it but take no action. And the benefit here is that event producers don't need to have any knowledge at all about who is listening to these events, and it keeps them very simple. And it means that other services can consume the events without needing to make upstream changes. So that's really interesting, but how do we implement that? How do we get the information from the left to the right without calling these systems directly? Well, for that, we need to have an event bus. So this provides an endpoint where an event producer can send the events, and the router manages directing and filtering those events to the appropriate downstream consumers. And consumers can get the events they care about reliably while the producers remain completely decoupled. So now our architecture looks like this, and the order service sends events to the bus, which is configured with rules that determine which downstream systems get the event. Now, some targets will only get some events, other targets will get all the events, but either way, the router now takes care of the complexity of ensuring that the events get propagated to the appropriate place downstream. Now back to our example now with an event bus and decoupling this architecture. It looks fairly similar, but now if the fulfillment service has an error, it just needs to raise an error event, and this is caught by the other services that are listening, and they can take action accordingly. Basically, the other system, the fulfillment system, when it fails, doesn't need to be aware of how other systems need to react to that. So in the other problem example, where a reward service is added, for another team to consume some sort of message from the order service, all they have to do now is add a new rule to the event bus. So there's no need to wait on the order service team to make an update for them. And now the service teams can act much more independently and move faster. So as your applications expand to include other systems and things beyond your immediate control, you need to pass information to and from these services. And most AWS customers now use SaaS products as a significant source of data in their systems. And so one of the problems with this is that since you don't own the code, it can be very hard to get at that information. So there's a couple of tried and true methods that people are mostly familiar with. The first is polling, where you might have something like a Lambda function that triggers every 5 minutes, every minute, every 10 minutes, some period, calling an API on that third-party application. And this is fine for some cases if your payload isn't too large, and basically if it's for very light numbers of changes. But it's very wasteful. You can find that many of those calls are coming back empty. And on average, if you have a distributed number of events happening, if you poll every 10 minutes, there'll be a lag of about 5 minutes before you know anything happened. So this is really a last resort option. And on top of everything else, you have to manage this Lambda service that's in place as well. So it's yet another piece of infrastructure that as developers you have to manage. Now option 2 are webhooks. And webhooks generally are a much better option. In this model, you provide an HTTP endpoint where a third-party provider can put or get information telling you about what changed. Now for this, you could choose to use a custom authorizer to validate the calls, and your data is much closer to real time. But webhooks aren't perfect either. They have some pros and cons. So yeah, they're closer to real time, and they're very simple to implement if they're supported by your third-party provider. And they're definitely more efficient than polling. But there are some cons. So if your service goes down on your side, chances are you have lost information if your provider doesn't know how to call you and retry you. These endpoints are internet-facing, so you have to secure them and do all the sorts of things you do with anything else you put on the internet. And often the security model that's used uses static secrets and things that aren't really ideal. And on top of that, of course, you still have to manage the API, and it can be very difficult to scale. So these providers can send you many, many events, and if you're not able to scale up, you'll either go down or you'll lose information. So can we do better? Well, we can, and AWS has a fairly new serverless event bus called EventBridge. We announced this earlier this year at the AWS Summit in New York. Now this is a serverless event bus service, which means that it finally makes events first-class citizens. You can ingest events from AWS sources, from your own applications, whether they're EC2 or Lambda-based, and you can also ingest data from third-party SaaS providers such as Datadog and PagerDuty. So this is not an entirely new service. It evolved from CloudWatch events. So even though it's fairly new in terms of the name, it's already processing trillions of events per month. And this is really just the beginning. There's a lot more on the roadmap for this product. Some of the things that are worth noting about this are that it's serverless, so we like that. There's no infrastructure to manage or to provision. Scaling is automatically handled for you, and you only pay for what you use. Right now, the billing is set to $1 per million events. You're not charged for events that are sourced from AWS services, and you're not charged for the delivery of events. The really key thing is that traffic this way travels through the AWS network and not on the internet, so that makes it inherently more secure as well. So how does it work? Well, basically, it all starts with an event source. So your event source can be any one of 95 AWS events, your Lambda functions or apps or other SaaS application providers. Now, if you use a SaaS application integration, there's a special resource called a partner event source that will appear in your account. And this basically is a logical connection between the SaaS provider and your account without needing cross-IAM roles or credentials. Next, you have the event bus. Now, if you've used CloudWatch events before, the default bus that you've used you'll be familiar with, but now you have other custom event buses that you can create, and the SaaS partner event bus that's available as well. Then there are rules, and this is really where the magic happens. So you associate the rules with your event bus, and we have complex rule handling that can let you specify matches on different parts of JSON, including nested attributes. And then you can directly send that to 19 different services within AWS, and you can have multiple targets per rule. So rules allow you to match against the metadata. So if we take an example event on the left here where a ticket was created, and we take an example rule, this would match because it's matching on the source and they're identical in both the event and the rule. In this example, where a rule is looking for events where a department is billing or its fulfillment, this also matches because the incoming event has a department of billing. And in this example, it would fail because the rule is looking for resolved tickets and the example event has a created ticket. Now, once a rule has done its work and either it gets forwarded onto a target or it doesn't, you can then associate which targets will then be receiving the event. And targets allow you to do things like invoke a Lambda function, or put a record on a Kinesis stream, or start the execution of a step functions workflow, or even start a task using ECS or Fargate. So enough with all of the arrows and boxes and PowerPoint. Let's have a look at how this really works. Okay, we're going to try this in a way that I've never tried it before. I can't see it at all, so here we go. So on the left-hand side, what you have here, this is a live SAM template that I coded up, so it's very, very simple, but it actually works. On the left-hand side, you have the order service that we talked about. And this would be a simple Lambda handler that's going to do some work, create your order, whatever it needs to do. And the code at the bottom is the tail end of that function. So it's going to build this parameters object and then submit the order, or submit the event to EventBridge. And at the bottom here, you can see that essentially it calls this EventBridge object, puts the event into the bus, and then you get a response back saying that the event has been durably stored. Now, in practice with production, you'd want to put a try-catch around this, make sure it works properly, but from the point of view of a demo, that's all you really need to be able to see. Now, in the middle, what you've got is a SAM template, and what this does is the first part defines the function and says that it's going to be called, and it has the access to put events. As Uri said earlier, don't use star permissions, so don't do that. But that does work. Then for the invoice service down here, this is the invoice function. This is on the right-hand side. So this function on the right is waiting to receive an event. Now you see from the function, it has absolutely no knowledge of the order service on the left. It's simply going to receive an event payload, which is going to be the JSON on the left. And then further down in this template, we see the rule, which I was talking about. And the important parts of the rule here are that it's going to match on a source, demo.orders, and look for a created attribute in the JSON. On the left, you'll see that matches. We have a detail type of new order, the state of created with demo.orders. And we've also got an ID of 123 as well. Now, in the rule, the target specifies that if this matches, it will be sent to the invoice service on the right. Now, when the invoice service on the right receives this, it really has no idea how it was called. It just received an event, and in my function, it's simply going to log that out, and that's that. So let's test this. It's really hard typing this way. So I'm going to trigger and invoke the function on the order service function. And you can see that that has now successfully stored the event in EventBridge. On the right-hand side, we're looking at the CloudWatch logs here. We're just tailing from SAM instead of going through the UI. It's been triggered. In the next few seconds, you will see the event be logged out in the console. Oh, it's already shown. OK. It's very, very hard to see. Yep. So it's really that simple. So essentially, when you decouple these services and you put EventBridge in the middle, you simply have that one-line call you're going to make in the originating service to put the event in the bus. The critical piece is the rule, and using CloudFormation and SAM to do this makes it very easy to build events on the fly. There's a couple of interesting patterns you can do this very, very easily. So if you still need to use a webhook, for example, you can put EventBridge behind your webhook. So if you have API Gateway with EventBridge behind it, that gives you an automatically scalable webhook endpoint. So if your downstream service is having a problem, it simply works at that point, and you're not being charged for ingesting the events because they're coming from API Gateway. But all you have to do is put these things in place and move towards an event model, and at this point you effectively decouple the service. Now this is asynchronous, so it does inject some latency into the process. You can expect about 300 to 400 millisecond latency as a result, but if you have a workflow that isn't that sensitive to the latency, this is a great way to separate your events out. So that's it. So my name is James Beswick. The presentation stopped working, so my contact details I'll put out separately. But if you have any questions at all, I'm happy to take them. Yeah. Yeah, that's a great question. So when I first picked up EventBridge, my first thought was, I don't see what the difference is between SNS and EventBridge. And as I got into it, I realized they're actually fairly different. So SNS allows you to fan out to hundreds of thousands of different consumers. With EventBridge, you can't do that. You couldn't go to that scale currently. You only have 5 targets per rule, so it's not really designed for that kind of fan out. SNS has some different endpoints, such as email and SMS messages, depending on which region you're in. This is much more about taking a rule and then filtering on the rule. Now, you can do some filtering in SNS, but it's not nearly as powerful as this. For example, one of the patterns I was playing with the other day, if you're connecting a Lambda function to S3, instead of having the issues where you have to create the bucket at the point where you deploy the function, or you have to limit the number of functions and not have overlap with prefixes and so forth, you can instead pass it through EventBridge, so you can go S3 to EventBridge to Lambda. Now, you can do the same thing with SNS, but with this, you could have many more targets, and you could completely abstract away the incoming event. But in principle, the two services do have similarities, but in practice, when you implement them, they are fairly different. Yeah, so if you've essentially got one producer going to hundreds of thousands or tens of thousands of endpoints, I wouldn't change the pattern there. But with EventBus, or EventBridge, although you have the ability to create custom buses, the idea is really you just use the default bus. So you'd have one bus where you throw everything into. So it's really thinking about having a multiple producer environment. Yeah. Yeah. That's a good question.
With AppSync as well.
Yeah.
If you look up for AWS AppSync real time.
Yeah. Anything else? No, okay. Yeah, if you have any questions after you think of, just find me. I'll be around here. Otherwise, you can follow me on Twitter at JBESW or contact me at jbesic@amazon.com. But thank you very much for your time. Really appreciate it.